Okay, let's dive right into this explainer and crack the secret codes of math. Look, if you've ever stared at numbers with those tiny little digits floating next to them and felt a sudden wave of panic, well, you're exactly in the right place. Today, we're pulling from a fantastic educational source to break down the sheer logic of exponents and powers. We're going to see that math really isn't about blind memorization. It's about beautiful, predictable patterns. By the end of this, you are actually going to understand the why behind all those rules you were just told to memorize in school. So, let me ask you a question. Take a look at this expression. We've got a 2 with a little 4 up and to the right. Now, if someone asks you, hey, what's the power here, what would you say? If you're thinking the power is the number 4, well, you're about to have your mind blown, because that is completely wrong. Section 1. The power misconception. Let's start by clearing up a massive misconception that even older students, and honestly, seasoned professionals, get wrong all the time. Here is the absolute crucial point. The 2 is the base, the 4 is the exponent, and it is the entire expression combined that we actually call the power. The big number at the bottom, the 2, is the base, that tiny number at the top, the 4, is the exponent. But the whole package together, that's the power. Technically, we should read this as 2 raised to the power of 4. But, over time, people just got lazy and started pointing to the little 4 and calling it the power. But now, you know the real secret. Section 2. Why we need exponents. So, why do we even need these cute little numbers in the first place? Did mathematicians just invent them to torture us on exams? Not at all. Just imagine trying to quickly read or even compare the massive weight of a planet like Uranus with all these totally confusing zeros. If you're a scientist, are you really going to sit there and count 20 plus zeros every single time you write a paper? No way. One slip of the pen, and you've literally shrunk a massive planet down to the size of an asteroid. It's just a nightmare to read and write. And that's exactly where this math tool comes in. Exponents act like magical math shrink rays. They turn impossible, giant numbers into clean, easy-to-read formulas. That giant string of digits, it simply becomes 8.68 times 10 to the 25th power. Boom! Instantly, you know exactly how massive this number is just by glancing at that exponent, 25. It literally makes comparing vast cosmic distances or even microscopic atomic weights an absolute breeze. Section 3. The core logic, laws of exponents. Now, to actually use this math magic, we just need to understand a few super simple logical laws. Remember, our goal isn't to memorize a dusty textbook here. It's to see the underlying logic. Instead of doing massive, tedious calculations, if the bases are exactly the same, you just add the exponents when you multiply and subtract them when you divide. I mean, think about it logically for a second. If you have 2 to the third power, which is just 3 2's multiplying together, and you multiply that by 2 to the second power, which is 2 more 2's, how many 2's do you have lined up in total? 5 of them. So instead of writing it all out every time, you just add the exponents. 3 plus 2 equals 5. And if you're dividing, you're essentially just canceling them out, so you subtract the exponents. It is simple, it's logical, and it's a massive time saver. Oh, and here's a brilliant cheat code for dealing with signs. A negative base with an even exponent becomes positive, but with an odd exponent, it stays negative. Why? Well, think of it as the buddy system. A negative times a negative is a positive, right? So if you have an even number of negative bases, like a power of 2, 4, or 6, every single negative sign finds a buddy to pair up with, and they all become positive. But if you have an odd exponent like 3 or 5, one negative sign is always left hanging without a partner, which drags the whole final answer down to negative. See? No memorization required, just pure logic. Section 4. The zero power mystery. Okay, let's tackle the biggest mystery. Your teachers probably told you that any number to the power of 0 equals 1, but they probably just told you to memorize it. Well, let's ask why and look at this undeniable pattern. Let's take a base of 2. 2 to the third power is 8, right? Drop the exponent by 1, 2 to the second power is 4. Drop it again. 2 to the first power is 2. Look closely at the answers. 8, 4, 2. Every single time the exponent drops by 1, the answer is just divided by our base, which is 2. 8 divided by 2 is 4. 4 divided by 2 is 2. So, following that exact same logic, let's take the very next step in the pattern. We're currently at 2 to the first power, which equals 2. Drop the exponent by 1 again, bringing us to 2 to the power of 0. What do we do to the answer? We just follow the pattern. We take the previous answer, which was 2, and divide it by our base, 2. And what is 2 divided by 2? It's 1. That proves perfectly why any number to the 0 power must be 1. It's not some random, made-up rule, it's just the inevitable result of a mathematical pattern. And you know what? This brilliantly illustrates why negative exponents create fractions. Let's just keep dropping that exponent. Below 0 is -1, so 2 to the power of -1. Following our unbreakable pattern, we take our last answer, which was 1, and divide it by 2. That literally gives us 1/2, or 1/2. A negative exponent doesn't make a number negative, it just means we're continuing the pattern of division. It flips the number right into a fraction. Man, it is so satisfying when math just clicks like that, isn't it? Section 5, the final form, standard form. All right, let's apply all this logic to real life by learning how to write numbers in what's called standard form. To tame those massive planetary weights and microscopic distances, standard form is basically the official scientific way to shrink a number so the front part is safely between 1 and 10. The rule here is strict, but super simple. You have a number m multiplied by 10 to a power. But that m, it cannot be smaller than 1, and it cannot be 10 or larger. It has to sit right in that sweet spot, like 4.5 or 8.2. Well, let's actually see this in action. To shrink a normal number like 6872 into standard form, we look for the decimal point. Now, it's hiding at the very end. We need our front number to be between 1 and 10, so we move the decimal left 1, 2, 3 spots. Boom, it becomes 6.872. Perfect. But we can't just shrink a number and pretend nothing happened, right? We have to balance the scales. Since we made the number smaller by moving the decimal left 3 times, we balance it out by multiplying by 10 to the positive third power. But for super tiny microscopic numbers, the exact opposite logic applies. Look at point 0.00004. This number is way smaller than 1, so we slide the decimal to the right to make it bigger. We jump 1, 2, 3, 4, 5 spots to get a solid 4.0. Because we artificially made the decimal number larger, we must balance it with a negative exponent, so we multiply by 10 to the -5th power. Sliding left gives a positive exponent, sliding right gives a negative exponent. It's just a perfect mathematical balancing act. So, you've just seen firsthand that math isn't about blind memorization. It is about beautiful logical patterns. We debunked the whole power misconception, we proved exactly why anything to the power of 0 is 1, and we mastered standard form just by following the logic. When you stop trying to memorize and actually start looking for the why, an entire new world opens up. So what other math mysteries are you going to solve next?